So welcome to our first Harvard Data Science Initiative industry seminar of the academic year. I'm Jen Chow. I'm Director of External Engagement, and I'm pleased to introduce today's speaker, Anupam Datta from Snowflake. So Anupam is a principal research scientist and AI research lead at Snowflake. He co-founded True Era, which was acquired by Snowflake, and previously spent 15 years at Carnegie Mellon, where he was a professor of electrical and computer engineering and CS. His work advances trustworthy AI, spanning explainability tools like Shapley values, fairness assessments, and robustness for language and vision. He's authored over 100 papers, chaired national efforts on AI trustworthiness, and teaches trustworthy AI at Stanford. So before I hand over to Anupam, I'd like to remind our audience that there will be time after his presentation for questions. Please use the Q&A function to send in your questions at any point during his talk. And please don't be shy. All questions are good questions. All right. Thank you and welcome, Anupam.
Thanks, Jennifer. It's a pleasure to be here. In my talk today, I want to get into how we can evaluate and grade agents, find out what their GPA is, if you will. And this will report on a set of research and product work we have done over the past couple of years. When I started looking at this space carefully with the rise right after ChatGPT came out, one of the things I did was to do a vanity search. So this is from 2023. And I asked, at that time, Claude 2, who are the founders of True Era? And this is what it came back with. It got my details correct, but these are not my co-founders. We were founded in 2019, not 2014, and we weren't acquired by SAS at all. So while it got some of the general structures right, like there were 3 co-founders, the space in which True Era worked, and so on, a lot of the factual information was hallucinated. I returned back to Claude more recently and asked the same question. And this time, it got all of the details right. It listed the co-founders correctly, their details are correct, and as well as True Era's acquisition by Snowflake. So what I want to talk about today is this journey that we as a community have gone through over the past 2 years, starting from where we started with just prompting large language models with questions back in 2023 to an agentic AI world. And what are some of the key insights, design patterns, and in particular, evaluation that has helped us get to a state with significantly greater trustworthiness. Not all problems are solved, but there has been very significant progress. And we'll look at some of those key innovations that we have seen in the community that got us from point A here in 2023 to point B in 2025. So if I think about, as we go along this path, we'll go through an intermediate but useful step between prompting LLMs to getting to the agentic AI setup of today. And this is realizing that if you think of my first example where there was a lot of hallucinations when I asked who are the founders of True Era, that the way these large language models are being built, they are being optimized to generalize well. And this process of training actively penalizes memorization. And this interface, this interaction between what general facts get learned versus what very, very specific facts don't get memorized is really murky. So for example, at that time, I had also asked ChatGPT who are the founders of Google, and it did get that right. even though when I asked two of the founders of Truera, I'd got it wrong. And the reason for it is that if there's lots and lots of instances of a fact in the training data, then that becomes a general fact that the model can learn. But if there's only very few instances of it, then it'll tend to generalize and not memorize. So based on this observation, one of the learnings in the community was that we want to focus large language models on general tasks like summarization and embedding generation, logical inference, planning, and so forth, and leave memorization to some other kind of artifact. And that led to the insight that LLMs need a knowledge source. And vector databases was emerging to gain popularity around that time, precisely to address this challenge that when it comes to very specific facts, that might be better handled through a knowledge base, potentially recorded as in a vector database. And that led to the rise of what is known as retrieval augmented generation, which I'm sure many of you are familiar with. So in this setup, if I were to go back to who are the founders of Truera question, one way to address it would be to take the website, say information on the website truera.com, chunk up those documents into smaller pieces, convert them into embeddings, store them in a vector database. And when the user comes in and asks a question like, who are the founders of Truera, the question gets translated into a query embedding. There's a retrieval or similarity search step here, which retrieves relevant chunks of documents. And then those get summarized by LLM to produce the final response. So if you look at this architecture, LLMs are being used for these general tasks like generating embeddings and generating the final summary, but the retrieval step is done using this external long-term memory, which is in a vector database. Since then, there have been significant advancements that go beyond this basic architecture. You can have more complex ways of indexing. You can have agentic loops that don't just do retrieval in one step, but might iterate on it, and so forth. But this insight has been quite powerful, and especially in settings where you have specialized knowledge, maybe in an internal corpus in an organization like a company or a university that's not publicly accessible, and you still want to be doing querying over those, setting up a vector database or hybrid search, which combines a vector database-based retrieval with keyword-based retrieval and does ranking and so forth on top of them, has become a powerful technique that's now widely used. That said, getting from prompting LLMs to RAGs doesn't completely solve the problem of even addressing the problem of hallucinations. There are a number of additional pieces that are needed to make further progress on this problem. Getting RAGs to work well require coming up with good ways of chunking. So if you have, when you're chunking up your, let's say, the documents on the Truera website into smaller pieces, if the chunks are too small, then they may not be big enough to contain the answers to the question you're asking. If they're too big, they might have a lot of irrelevant information. So figuring out the right chunking strategy becomes important. The quality of the data here, how good the embeddings are, the results of the search quality, understanding queries well, and finally, in this final response generation phase, when you are using the LLM to summarize the results of your search, which could be a set of documents, that hallucinations can still creep in at that stage. With that observation, a couple of years ago, we introduced this notion of the RAG triad, which is a canonical way of evaluating the quality of various steps in retrieval augmented generation. It very much follows the architecture of how a RAG works. So when the user comes in with a query, and then there's a retrieval step, and you get a set of results or contexts out of the vector database, you can compute this evaluation, which is examining for each retrieved piece of context or each retrieved search result, how relevant is it to the query that was asked. So if you have 4 search results, for each of them individually, you can ask how relevant is it to the query that was asked. And this evaluation can, in some cases, be done by comparing the results with a ground truth data set where ideal results are available, or you can use an LLM as a judge itself to do this evaluation. And there are various trade-offs between these methods that I'll get into in a minute. Similarly, for the response generation step, when the final response is the summary of these retrieved search results, you can do a groundedness evaluation, which is asking for each claim in the final response, can I find support for it or evidence for it in the retrieved search results? In essence, we are asking for citations to information sources that we trust in order to solve the hallucination problem. So if you think back to the founders of Tuera question, the answer that we first got from Claude 2 years ago, ChatGPT, did not have this kind of citations. And in some cases, they were hallucinated, where it got my co-founders' names and details wrong, for example. Whereas if I look at the results from Claude right now in 2025, you will see those citations to documents, which is saying, here are the details for me, and here's a link that you can click on to go to the document which supports this summary claim. And that's where we have seen groundedness evaluations, not just, although the origin of these ideas were in the context of retrieval augmented generation, they have carried over to the world of agents, which are also doing retrieval-based operations. And so there is a source that you can go back to support your claims. And then finally, the third pillar of the RAG triad is answer relevance, which is measuring, is the final response, so the final answer, relevant to the query that was asked. And in some ways, these are measuring somewhat orthogonal elements. They are related in some ways, but are also looking at collectively giving a form of consistency measurement of the overall performance of the RAG. And part of the reason I'm covering this, although the talk is about agents, is that these metrics tend to be very useful even when you're measuring the quality of agents and trying to understand how good their intermediate results or final responses are. So the ideas have survived and have carried over to the world of agents. I want to spend a minute here to just give you one kind of high-level view of evaluations and the space of evaluations, which I often think of in terms of 2 axes. On the x-axis is how meaningful is the evaluation? How much can we trust the evaluation itself? Further to the right means it's more meaningful. And on the y-axis is how scalable is it? Is this something that we can use in large-scale systems? And what I find is that often when we are building LLM applications, whether they are summarization or RAGs or agents, it's very helpful to start with a small curated set of ground truth evals from domain experts potentially who understand the area well. And then that seed set becomes a good way to get started. And this could be in some cases 50 or 100 examples or a couple of 100 examples. And it's a good starting point, but it's hard to end there because it's expensive. It takes time and effort to curate a manual data set, ground truth data set. So on the y-axis, this does not do so well. but it's a very important part of the workflow of building and evaluating LLM applications and agents. Once you have fielded your agents, you can also get evals from the users of the system, where the users might have a box where they can give a thumbs up, thumbs down, or even textual description on how good the behavior of the application was. So that gets you a little more scalability, but now instead of relying on experts to produce the data set, you're relying on users of the system who might have less expertise. So we move a little bit to the left on the meaningful axis, but we are moving higher up on the scalability axis. Traditional NLP evaluations like BLUE scores and root scores that some of you may be familiar with tend to be too syntactic. So while they scale well, these are fully automated evals. They look for syntactic similarity, let's say, between the original document and its summary. Because the LLM might, in the process of generating a summary, might completely change the way it talks about it, although the semantics might be similar, the syntax might be very different. So these tend to not work so well in terms of providing meaningful evaluation, although they scale well. And then LLM judges have shown a good amount of agreement with human evals, often in the 80 to 90% of the judges designed well. They are expensive. So there are some trade-offs there, and you do have to spend a good amount of time setting up the judges in the right way. But that offers an interesting trade-off space where there's an automated evaluation. You can get quite strong agreement with human evals if you do it well, but it also tends to be expensive. And it gets to about the 80 to 90% agreement with humans, which is also where human-human agreement lies in a number of different studies from various research groups. And in some cases, it's possible to build medium-sized or smaller language models to act as judges. They might have to be fine-tuned, and there's more work in making them work well, but they can be more scalable, less costly, lower latency. So now let me go back and give you one concrete example of a groundedness evaluation and how it might help with building confidence in the final responses coming out of LLMs or RAG-based systems and agents and so on. So here's an example. The details are not so important, but up here is the transcript of a phone call where a person is calling room service in a hotel, and then there's a summary. And then the evaluation, the way it works is that for each sentence in the final summary, it's providing a score on a scale of 1 to 10 on how well supported it is by the original call transcript. So the first and the third sentences our clauses are well supported, but the middle one is not. So that's the kind of information that you might get through a groundedness evaluation, where you can get citations back to the original source in a fine-grained way, along with the score that helps understand how well it's grounded. The final claim is grounded in the source documents and in the information in them. So I want you to keep this in mind, because these are things that we'll start using as we transition to agents. So with that intermediate step, and a lot of this work on RAG-based evaluations and the RAG triad, we have been doing in open source in our TrueLens open source project. So you can go to the GitHub, and I'll share a QR code in a little bit and play with and use it in your work. It's a permissive MIT license, so you're welcome to use it in any of your research or commercial use as well. So now let's make the transition from RAGs to agents. And if I go back and look at this output from Claude with this is Sonnet 4, in response to this question on who are the founders of Truera, there are some things here that I want to draw your attention to. One is, after it describes provides a description about who I am, it has this link that you can click on and go to this news article, which talks about the Snowflake acquisition. And this is where the groundedness evaluation is happening. So in the back end, you could have an automated evaluation that finds this, traces this claim back to specific sentences in this news report. The overall response, this final answer, can also be evaluated with answer relevance to assess how well it answers the question that is being asked, which in this case, it does a good job of. And then for context relevance, we'll assess for each of the intermediate results that were search results that came out, how well do they support, how relevant are they to the original question, right? So I have not clicked in the screenshot, it's not so clear, but if you see the 10 results here, they're actually, the agent is going out and doing a web search, it gets back 10 results, and each of those results you can think of as a retrieved context for which you can assess context relevance. Great. So if I were to take a step back, when we think of agents, there are a few building blocks. Agents will plan. So in this particular example, they plan, they use tools, they reflect, they use some memory. And then there's also agents that make use of multi-agent collaboration, where it's not one agent that's performing actions, but a collection of agents that are working together with separate division of responsibility to accomplish a bigger task. So if you think back to this example and think of the agent building blocks here, when the agent gets the user query, that's the goal that it is trying to now respond to by coming up with an answer. It plans and it thinks through, and it might say, okay, in order to find this information, it's better to do a web search to see what sources I can get, and then I'll make a call. So that's the planning step. Then it makes use of tools to execute on its plan. And the tool in this case is like a web search API that it can call, and it gets back a set of 10 results. Then it reviews each of these results, reflects on them, and then assesses, is there sufficient information here to answer the question that I'm trying to answer for the user? And that's the reflection step. If in that step it finds that there isn't adequate information, it might replan and come up with an alternative way of finding this information. In this particular instance, it finds the information, then it generates a summary, it includes citations, and so on. So this already makes use of planning. It makes use of tools like web search. It's reflecting on the results. For more complex tasks, memory can be useful, where it saves relevant information of all the things that it has done, so that it keeps track of things that it needs to remember as it's going about its job. And I'll get to an example with multi-agent collaboration in a little bit. I want to sort of introduce some terminology here. The agents that we have been talking about, there's lots of different types of agents. There are coding agents like Claude Code and Cursor and so on that some of you may be playing with. But my focus today is on data agents, where a data agent you can think of as an autonomous or semi-autonomous system that connects to various data sources like databases, APIs, files, streams, the web. It understands queries expressed in natural language or even code. It can plan and perform actions such as query decomposition, where it takes a more complex query, breaks it down into parts. It can retrieve data like from the web or from a structured database, or do search over unstructured data like in the RAG setting. It can analyze data, visualize it, potentially by writing code. And you have seen some of this it can also provide insights or takes decisions based on the data. And I'm sure many of you have seen these kinds of agents in action, or even using it in your day-to-day work, where deep research from OpenAI, or there are similar versions from Anthropic and Google and so on, are one class of data agents. At Snowflake, we have also been building a data agent that we call Snowflake Intelligence that can take natural language queries and then in the back end make use of tools that allow search over structured and unstructured data in a seamless way. So that's another example of a data agent. You can go play with it. It's in public preview right now. As I introduce a bit more of the concepts of how to go about evaluating the quality of these agents, to go about building trust that these agents are behaving as expected, I want to use as a running example this simple LangGraph agent. Later on in the talk, I'll also share the notebook for folks who may want to try it out hands-on. But the agent takes natural language queries like the one here, which says chart the market capitalization in USD of the top 5 US banks. And then it goes through a few different steps to produce the final response. It's a multi-agent system. There are a few different agents here: the planner agent, the executor agent. There's a web researcher, which issues search queries over web search APIs. There's a chart generator that will summarize the results, numerical results into charts. There's a chart summarizer, which looks at a chart and then writes a natural language description of the key takeaways from the chart. And then there's also a synthesizer, which in the case the executor makes use of the web researcher to generate find sources of information, might look at 5 different sources and summarize it, much like we saw in the Claude Sonnet example, where there were 10 different results that came from a web search on both the founders of Troira, and they were synthesized and summarized at the end. So that's the structure of this multi-agent system. The planner takes the query, does the planning of how to go about answering it, and then the executor calls various tools or sub-agents to generate some of the intermediate results, and then it controls the execution flow and goes back to the planner if needed, if there's replanning needed. So those are the building blocks. The tool use is done with the web researcher makes use of the Tavily tool to do web searches over a web API. The charting agent uses chart generator uses a Python tool, and each of these steps there's some reflection that's done by the executor and planner to decide if enough information is coming from has been acquired through the web search that it can now go to chart generator, for example, and so on. So that's the setup. And as we think about it, maybe now we have a concrete example to be thinking about, and I want to take a step back and abstract a little bit from this specific example and think about what are the key concepts here behind how agents work. And I'll distill 3 key concepts here. One is that the agent will often have a goal. The goal in the case of the deep research or web search agent is to answer a user's query. And you could have other kinds of goals depending on the agent. Then it plans, comes up with an initial plan to achieve that goal. And then it's going to act in accordance with that plan to achieve the goal. And after some set of actions, the control goes back to the planner to review how much progress are the actions steering in the right direction. Should it continue with the current plan? Should it update its plan? And so there's an iteration loop between the planning and action stage. And our interesting insight or observation here is that agents work well or are trustworthy when they execute with their goals plans, and actions aligned. Or in other words, if the agent's plans or actions are not aligned and goals are not aligned, then you see a bunch of different kinds of failure modes. So this goal plan or action alignment, or GPA, is informs how we want to go about measuring how trustworthy our agents are. So that is one key insight that we have. And now let me elaborate on that a bit to make this more precise. So one way to think about this is these three pillars of goals, plans, and actions are how agents operate. And our thesis is that evaluation should also make use of this insight about how agents operate, because that will then help us think about failure modes in a systematic way and inform improvements to agents' behaviors. So what are the various things that we may want to measure that will contribute towards the agent's GPA? First is goal fulfillment. Goal fulfillment is measuring, and our measurements will be post hoc, meaning that the agent has executed, we have an execution trace, and we are asking, given this trace, various kinds of measurements, but let's start with goal fulfillment. We'll ask, does the agent execution trace or sequence of actions that it has done, how well does it achieve the goal that it was meant to be? And a concrete instance of goal fulfillment is answer relevance. So if you think back to our question of who are the founders of Truera, is the final answer actually relevant? Comes back to, is it reporting information about who the founders are? Groundedness could be another thing that you measure at the end to assess goal fulfillment, meaning that for each claim in the final response, the three different founders, is that supported by a source that was gotten to through the retrieval steps. Right? So that's the first thing you want to measure. That's goal fulfillment. And it requires examining whether the kind of goal fulfillment metrics you define can be different based on what the agent is supposed to, what the agent's goal is. But two examples could be answer relevance and groundedness. Next up, I want to talk about logical consistency. So logical consistency sits at this intersection of goals and plans and actions, and it's looking for whether the agent's behavior and execution is consistent. It's looking for some form of internal consistency. So for example, if the agent has said one thing at one point and later on it says something that contradicts it, like let's say it says at one point that today's date is September 18th, and later on it says that today's date is August 15th, then that would be an example of a logical inconsistency. Or the inconsistencies might arise between plans and actions. In the planning step, it might say, let's go ahead and do this particular action. And then later on, when you look at the action, sequence of actions, you might see that that action was missing, that something else got done instead. So logical consistency, in some ways, if it's properly set up, the intent of it is to capture all kinds of internal inconsistencies that the agent has between its planning and its actions and its goals. And if it's designed in the right way, it could capture all kinds of quality issues that an agent suffers from. An orthogonal evaluation is execution efficiency. This gets at whether the agent took the most efficient path to achieve its goal. With the benefit of hindsight, if you look at an execution trace, execution efficiency may be low if we observe that the agent could have taken just one loop here and gone through but it kept looping around, doing a bunch of redundant actions before it proceeded. So that would be an example of an execution efficiency of a trace on which execution efficiency would not be that high. So quality or trustworthiness is one pillar, execution or efficiency is the other. For an agent to get a good grade, we want it to be both achieving its goals in a qualitative sense, achieving the goals that it's designed to achieve, but do so in a way that's also efficient. Next up is plan quality. So logical consistency and execution efficiency could potentially work just with access to the execution sequences. But if you have access also to the plan that the agent came up with and then updated as it went about its execution, then you can ask questions about how good was that plan. Is it a good plan for achieving the agent's goal? And so plan quality sits at this intersection between goals and plans and measures how good of a plan it is or how good of a replanning step it was in terms of steering the agent towards achieving its goal. And one special case of it is tool selection, where tool selection is measuring if the agent selected the right tools in the right sequence in order to achieve its goals. And for all of these evaluations, we can do the evaluations through setting up ground truth data sets for an agent, but we also have done work on creating LLM judges that can do these evaluations automatically. And finally, at this intersection of planning and actions, there's a plan adherence related evaluation, and it measures whether the agent's actions follow or adhere to the plan that it came up with. And one special case of it is tool calling, which measures if the agent called tools in the right way with the right parameters so that the tool execution proceeds in the expected way. So the interesting thing you'll observe is that all of these sit in these intersection areas of alignment between goals and plans, goals and actions, plans and actions, and in some cases, alignment across all of these three. So let me quickly summarize some results that we have, empirical results. So we built this agent GPA framework in the TrueLens open source project. You can go play with it. We have validated it on 2 data sets. There's a Trail GAIA open source public data set for a multi-agent data agent kind of setup. And we also have done some work on an internal data set for Snowflake Intelligence. And our first key result is the agent GPA framework provides a systematic way to cover a broad range of agent failure. So we have come up with this framework. Conceptually, it sounds interesting, but how well does it work in practice? So we tried it out on the Trail GAIA data set. We split it into half of it into a dev set and the other half into a test set. And on the test set, when we ran the evaluations, there were 281 agent internal errors. And if we think of these categories as being the evaluations, and the ideal evaluations are done with humans who are categorizing each error into these categories that we have defined, then we find that a human annotator can take all these agent internal errors and put them into one of our 5 different categories. So that shows a form of coverage or completeness of this framework to capture agent internal errors. And by internal errors, I mean errors that the agent has agency over, if you will, and control over. It's designed to do well on these things. There are things that the agent cannot do sometimes. So for example, if an API call is failing because of rate limits on the API and too many calls are being made to a large language model, that kind of error the agent will usually not have agency over, or if there's a power outage, it won't be able to recover from it. Those are not covered in this framework. The second key result is the LLM judges that we have built for measuring agent GPA show strong agreement with human judgments. And quantitatively on the trail GAIA dataset, there's a 94% agreement. So out of the 281 examples in the test dataset, 264, there was agreement between the judges, LLM judges assessment and the human annotations. As a point of comparison, the baseline here is that the trail work itself has a LLM judge that shows about 55% agreement on the same 281 examples. On Snowflake Intelligence, we also got encouraging results. There's 82% agreement when grading on a 3-point scale. By a 3-point scale, I mean that the judge is either grading an evaluation as where the agent got it totally incorrectly, partially correct, or fully correct. And then 2-point scale is just incorrect or correct, where the two different forms of partial correctness and total correctness are grouped into one bucket. And so there's 97%, here there's 82%, which are in the zone where we can be comfortable using LLM judges, because as I said earlier, human-human agreement is also in the 80 to 90% range. Finally, the third key result is that these LLM judges for measuring agent GPA localize errors with strong agreement with human annotation. So the previous result was the error caught? And then this result is about not just whether the error was caught, but did it localize it to the right step in the trace or right span in the trace? So the trail GAIA dataset actually has that kind of localization information. And we got about 85% agreement with the human localization work. As a baseline, the trail LLM judge shows 49% agreement. So this was a big step up. So these results provide additional empirical support that we are onto a framework that has good coverage and that judges have good alignment with human agreement. So the arc of science is moving in the right direction. I want to point you to some additional resources that you can play with. We have this example LangGraph agent that I mentioned, which was built with the LangGraph open source library and evaluated with TrueLens. There's a notebook as well that you can play with. I just want to show you a couple more concrete examples just to build some intuition about these agent evaluations. So we'll work on this example and this query, which is chart the market cap in USD of the top 5 US banks. And then let me show you what it looks like in the TrueLens dashboard when you run the evaluation. So this is a screenshot from the TrueLens dashboard, which you will get if you run that notebook. This is the question, chart the current market cap of the top 5 banks in the US. You can see the output here, which refers to a visualization. And then the various agent GPA evaluations are down here. And then if I drill down, we can see what the form of the evaluation looks like. The execution trace is on the left panel. On the right panel, when you click on one of these thumbnails for evaluation, you get more information about it. So the plan quality in this case was 1 on a scale of 0 to 1. So that's a good plan. And if you look at the supporting evidence, it talks about the plan having 3 steps and that all of these steps are logically ordered, they're necessary. So there's no unnecessary or missing steps. So this was a good plan for achieving this goal of answering this query. On the other hand, when we go to plan adherence, it gets a grade of about 1/3, about 33%. And if you look at the supporting evidence, it says, well, the plan had these 3 steps. However, while step 1 and 2 were correctly executed, step 3 which requires the chart summarizer to provide a concise narrative summarizing the differences in market cap, that step was not properly completed. The trace shows the chart summarizer node was called, but no summary was produced or included in the final output. So this is the reason why plan adherence is low, because only 2 out of the 3 steps were done. And the third step was an important step. So there's a penalty here and the grade goes down. And because the answer relevance depends on the final summary step, this third step being executed well, the overall answer relevance also goes down. It's a little unfortunate because it had collected all the intermediate results. So context relevance is high, but the final answer did not do a good job of summarizing all of that. That's why the answer relevance goes down, and it's because of this plan adherence. So you can see that this evaluation is helping kind of pinpoint exactly where the source of the issue is. If you just saw a low answer relevance score, then that doesn't tell you which step failed or why the answer relevance is low. But when you see low answer relevance, but good context relevance, that's saying that intermediate results were great, but the final result was not. And it was because of this failure of plan adherence, and in particular, that final step. So this is how the evaluations can be very helpful in localizing errors, which can then suggest improvements that you can make to the agent by adjusting its prompts and so forth. Logical consistency is also good here. I'm mindful of time. Execution efficiency also is good. So let me summarize now and leave some time for questions. What we discussed today was this evolution over the last couple of years from a world in which we were prompting LLMs, like in ChatGPT or Claude, to answer factual questions where hallucinations were quite common, and the insights and design patterns that got us to the current world where there's been very substantial progress, not just in the models getting better, but through having support for tool calling and retrieval and planning and reflection and adding in citations to do groundedness evaluations and so on. We have gotten to very significant improvements in data agents and other spaces within agents as well. And one of our key contributions and insights when we were looking at RAGs was the RAG triad. And today, I wanted to introduce this concept of measuring an agent's GPA or goal plan alignment. And we talked about a whole bunch of evaluations that look at failures. You can follow this QR code to go get access to TrueLens and play with it. And we also talked about a bunch of empirical results that validate the power of this framework. And next week on deep learning AI, we'll have a new course called Building and Evaluating Data Agents that'll be open and free. And we'll have notebooks and such to play with. If you're interested, please join us at it. Thank you so much.
All right, thank you. So I wanted to turn to some of the questions that our participants are asking. And one question is sort of a little bit fundamental. Konstantina Yaneva asks, could you talk about the difference between RAG, MCP, and agent with tools? The clear distinctions between these and how they access data are a little fuzzy for me. I would add also, when you're thinking about how those tools stack together, what are the risks that you're thinking about in terms of how the workflow can help mitigate risks?
Sure. Sounds good. Yeah, so let me first take the question about RAGs versus agents and where the distinction is. So if I go back to my RAG slide, the typical architecture of a RAG is like the one here. It's a fixed control flow where when the user comes in and with a question, it gets converted into embeddings. There's a retrieval step and a summarization step. So the control flow is fixed, and there's a very specific tool, if you will, that it uses, which is retrieval over vector databases. And that has gotten augmented a bit. So it's these days in practice, people don't use vector database in isolation. They tend to use a hybrid search paradigm, which combines search over vector databases with search over like keyword search, more traditional search, and then some re-ranking. But nevertheless, a useful abstraction to think of it is think of in this context is that it's a fixed control flow, number one. And number two is that it's making use of one tool, if you will, the search or retrieval tool. If we go to agents, agents generalize from there on several dimensions. You could take a step back and think about it. The control flow in an agent is not fixed. There's actually a planner or orchestrator that in data agents, based on the query, it'll dynamically come up with a plan of which tools to use to figure out parts of the answer, which it might then combine to respond to the final answer. So there's two dimensions of generality here, the dynamic planner as opposed to fixed control flow. And there could be any number of tools, not just a specific tool for search over unstructured data. It makes use of reflection as well, which is it reviews the intermediate results and then can adjust its plan to explore new things. And you'll see that a lot when you use deep research-like systems. And then finally, it can make use of multi-agent collaboration, like we saw in the line graph example. So these are all dimensions of generality that agents introduce. But at the same time, now coming back to your question, Jennifer, it also introduces new kinds of risks and issues that can surface. When we were talking about how RAGs might fail, these were the three metrics that we were thinking of as getting to the core of failure modes. The retrieval might fail, might produce irrelevant answers, which we want to catch with context relevance. The final response might have hallucinations, which we might want to catch with groundedness. And even if the response is grounded, the answer might be irrelevant, which we catch with answer relevance. But when you get into agents, there's a lot of other failure modes. The goal fulfillment is where the final response being relevant and grounded sits. So it's capturing this piece. But because the control flow is much more dynamic and is being generated by the agent orchestrator, the quality of the plan itself that the agent comes up with might be poor. And if the quality of the plan is poor, then you might end up not achieving the goal well, or you might be taking inefficient paths to achieving the goal. So that's a whole other set of issues that don't arise at all for RAGs because traditional RAGs are fixed control flow. There can be issues with adhering to the plan. Like in the example that I was showing you towards the end, the agent came up with a good plan, but the plan quality was good, but when it executed, it did not do a good job on the third step of the plan. It didn't follow through on it well. And because of that, we didn't get a good response and the answer relevance ended up being poor. So because agents have these additional steps of planning and reflection and tool use, there are all these additional kinds of failure modes that arise in the trajectory of the agents itself, which these additional evaluations catch. There's a whole other set of issues around adversarial attacks and security that I didn't even get into in this talk, but those are a lot more prominent for agents because they and maybe this is a good time to connect to the MCP part of the question, which is when we talk about calling tools, in the examples that I'm using right now, the tools are called by directly calling APIs like the Tavily API and so on. But the challenge with that architecture is that every tool might have its own idiosyncratic API. And so from an engineering standpoint, it's a lot of work to customize the tool calling for this diverse set of APIs. What MCP does is provides a uniform protocol for setting up MCP servers. So Snowflake has an MCP server, for example, with its tools, and Salesforce has its own MCP servers with its tools. if I'm building an agent that wants to call tools from both of these companies, there's a uniform way of doing it. So I can write my agent in a very general way, and it becomes much, much easier to keep adding more and more tools as they become available. So that's where MCP adds a new kind of value. And it's valuable from like an interoperability standpoint, because one of the things that we have seen is cloud providers, for example, historically have built their own stack. So if you're in AWS or in GCP, then the vertical stack, if you want to go across AWS and GCP, then it's kind of hard, right? Similarly, data formats historically have also been proprietary, but now we're moving towards more open data formats. And what many large companies and enterprises are asking for is not to get locked into a specific agent building framework. So for example, if I have a team that's building with, say, Snowflake's agent API, and another team that's building with a LangGraph, then it's very easy now through MCP for the team that's working with LangGraph agents to call tools that are built over the Snowflake API using MCP. So that's the form of interoperability that the motivation for MCP is.
Yeah, I think the question of interoperability comes up quite frequently across the many domains that HDSI works in, and I think so. So it's an ongoing challenge in terms of enabling that. I think you've talked about this a little bit as a final question. You've talked about how GPA metrics capture the different types of the agent failures. Obviously, that was the discussion. But what you did talk about is how the metrics could be used for part of the training and optimization loop to improve agent performance sort of at the get-go. And I'm wondering if you could just expand a little bit more on that.
Yeah, sure. Yeah, that's a great question. So for example, what we can see through these processes could helps with localization of errors. So let me give you some concrete examples. So let's say tool selection fails. And through the evaluation, we see that there was a particular step in which the agent did not pick the right tool. It should have picked tool A, it picked tool B instead. And this evaluation is helping us localize to that step and say, this is a step where it failed. Now, if you examine that step, what you might find is that the tool descriptions were not very good. They were written in a way that there wasn't enough information for the agent to disambiguate between whether tool A is the right tool to call or tool B is the right tool to call. So then the improvement would be in this case to adjust the tool descriptions, make them more informative so that the selection process can improve. There's more information available for the agent to select the right tool. Another kind of example could be that often in agents, what we have found is that actions tend to be recorded on the trace, but not plans, or maybe partial plans are recorded, but not complete plans. You can still run evaluations 1, 2, 3 if you just have actions, but having a more explicit plan recorded in the trace helps with observability and debugging because you can narrow down and see exactly where things are falling. So for example, in the running example, I showed a failure of plan adherence, where there were 3 steps in the plan, but the third one didn't get done. And that's because the prompt for the summarization of the chart was not that great. So then that suggested the specific place to focus on to improve it was to improve the prompt of the chart summarizer. So that's kind of the general nature of improvements where through the localization process, you can see what's the root cause of the problem. And then based on that, there are ways of improving tool descriptions or prompt optimization. So it's a form of evaluation guided optimization, if you will.
This is all really incredible and useful in terms of these agents are coming online so quickly, and everyone is sort of in that space currently. You know, how do we begin to adopt these? And so, I think embedding observability makes a lot of sense in terms of in terms of the responsibility that we have to make sure that these things are running appropriately. Um, the final question that I ask as part of this series is any resources that you have that you recommend for continued learning in this space. I know you mentioned an upcoming workshop. Could you share any other resources that that you recommend?
Yeah. Yeah. So this QR code will take you to the TrueLens website, and TrueLens has a lot of this information on how to run Agent GPA is available on TrueLens. And then this deep learning AI, it's an open course that I co-taught with Josh Riney. Andrew Ng did the intro for it. It'll come out next week. It's a open free course and lots of good resources there, hands-on notebooks and so on, if you want to try it out yourself. Those are some good resources to get into the next layer of detail.
All right. Well, thank you. Before we close, I'd like to mention that our next industry seminar will be October 16th at 1:30 p.m. with GE Vernova. Registration is available on our website, datascience.harvard.edu, and through our weekly newsletter. We hope to see you there. So with that, thank you so much, Anupam, and thank you to our participants for your good questions, and we hope to see everyone soon. Have a great afternoon.
Thank you so much.
All right.